Is my screen visible? Okay. So good evening. And in previous class, uh, I have discussed about the different types of image, how we will create an image, and now we are moving to the different types of digital image. The digital image depends upon the color. What type of color we are using, that define the types of digital image. In digital image, we use uh, generally color image, or sometimes we use monochrome or gray scale image. What is the difference between this gray scale color image and gray scale image and monochrome image? If we take the image of any object, if we take the image of any object in a single color, so for single color it is called monochrome, and it uses only single bit. It uses single bit. So if it use if it uses single bit, it means it has two different states. Either that may be on or off. The bit may be either on or off, because each single bit has only two different states, either on or off. On means white. On means white, and off means black. Off means black. So for monochrome image, or sometimes it is also known as binary image, because each monochrome monitor has single color, and that color is fixed, and that one is either black or white. So this type of image is called binary image, that uses single bit to represent each pixel. There are a different number of pixels. These are our pixels, and these pixels has either on or off value. It means it uses only single bit, and that single bit may be either on or off. On means white, or off means black. That I have discussed in the previous class. The representation of t on a graph paper or on any screen is represented as either 0 or 1, but it may also include the color. If it is monochrome color, then it is only in on and off form, and on means white and off means black. But if we want to different color, then we use gray color or gray scale image. In gray scale image, suppose I take a color black. You may take any other color. Suppose I use the black color, then deep black and lighter black and more lighter black. This type of black image may be produced, and this complete different values is based on the number of bits. To represent the gray scale, we use 8 bits. We use 8 bits. 8 bits means 2 to the power 8, and 2 to the power 8 means it has 256 different values. It means this black color has different values from 0 to 255. This 256 may be range from 0 to 255. 255, where 0 indicates black. 0 indicates black and white indicates white. Sorry, 255 indicates white. This is the extreme point. So if we use 8 bits in place of single bit, in monochrome or binary image, we use only single bit. But in case of grayscale, we use 8 bits. And this 8 bit produce 2 to the power 8, that is 256 different values. And this 256 has different range from 0 to 255, in which 0 is known as a black and 255 is known as a white. And between from 0 to 255, I means from 1 to 254 are the different values or different intensity of this black. So this type of color that has only black color, but the intensity of black will range from 0 to 255. 0 means complete black, 255 means white, and 1 to 254 is less black than this 0. So 0 is the maximum black, 1 is less than 0. 254 is almost whitish or blackish color. So it has total 256 different intensity of black. We can choose other color at this place. We can use either green or blue colors. Only one color is taken, and that color has 256 different intensity. So this type of principal color or image is called grayscale color, in which 8 bits are used, and 2 to the power 8 means 256, and it ranges from 0 to 255. So the difference between grayscale and monochrome, the difference between this grayscale and monochrome is, monochrome or binary image has single bit that has only one color, and it has two different states, either on or off. But in case of grayscale, it uses 8 bits, and due to 8 bits, it has 256 different color, different intensity of the same color, like black or green, and in which 0 is the black. If we use black color, then 0 is the black and 255 is the white. And range between 0 to 255, that is 1 to 254, are the different intensities of this black color. So this is the gray scale color or gray scale image. But there are another type of image that is called color image. In this color image, there are different models. In color image, there are different models. Among them, the RGB model is mostly used in our system. In RGB model, the R represents red, G represents green, and B means blue. These are the basic color of any color systems. So red has 8 bits, and green has also of 8 bits, and blue is also of 8 bits. So if we see the total number of colors produced in color is 8 into 8. 8 into 8 2 to the power 8 into 2 to the power 8 into 2 to the power 8. So we have millions of colors. We can produce millions of colors with the help of RGB. The value of R is from 0 to 255, 0 to 255, and the green value has also 0 to 255, and blue has also 0 to 255. So if we combine all these colors, we get about million colors, and our eye can recognize only some of them, not all colors. So it produces maximum colors. So we use this RGB model. And in this RGB model, there are two different subcategories. And that categories is that color image may be either full color image, uh, and this full color image is used in our TV systems. In our TV systems, we use full colors. Any colors that is produced by RGB can be used in our TV. But there is one another type of color that is called pseudo color. To a particular monochrome intensity or range of intensities, it is like a gray scale. So in pseudo color, we select some random number or some random color. That color will be used in either monochrome intensity or a range of intensities. So this can use different types of random values. It depends on the users. You can use any color, and that color has either single intensity or range of intensity. So it may be also considered as a part of gray scale. So these are the two different subcategories of color image. So we can say there are basically three types of image. First is either monochrome or binary image. Second is gray scale image, and third is color scale image. We can use any, but generally for theory purpose or any other purpose, we use gray scale color. And after studying this gray color, we use all other colors for our purpose or for our requirement. Now we move to the image sampling and quantization. These two topics are very, very important for image processing. First, we take the object, and we produce the image of this object. This is our object. This is our object, and we produce image, and this image may be of different natures, and this image is digitized. This digitization is done with the help of sample and quantization. So image representation of 3D object in 2D is an image. This object is in our real world. Any object that is placed or that exists in our real world is in 3D. And as I have discussed about the projections, if we draw the image of this 3D object, if we draw the image of this 3D object by using some projection, that projections may be either perspective projections or orthogonal projections or multi-view projections, etc. If we produce the image of this 3D object in 2D image, 2D image. Since I have already discussed that the image will be one less dimension, image will be in one less dimension that exists in our real world. If our object is in 3D, then its projections will be 2D. And if it is our object is in 4D, it means its projections will be in 3D. Similarly, if our projects, our real world or object is placed in n dimension, then for n dimension real object, we produce n minus 1 d image. So this is the relation between a real world object and image. Image is always one less than the real world dimension. So this is our real world dimension, and this is our image dimension. So in image dimension, due to these projections, one less dimension is used. So image generally, we use the image, that is representation of 3D object in 2D is an image. So 3D objects will be in 2D image. And after getting this object, we apply sampling. And after sampling, we quantize it. Then sampling plus quantization is called digitization or digital form. So if we can draw the object, suppose it is our object. This is our object. And this object is in 3D. Then on this 3D object, we apply some projection that I have already discussed. We apply some projection or some techniques that will produce the image of this object, that is 2D image. This is our image. And the dimension of this image is one less than the real world dimension. So it is in 2D dimension. Then on this image, we apply the process of sampling. We apply sampling that I have already discussed in earlier class. And after sampling, we quantize it. Quantization. After quantization, get the digital value. Then we get the digital value. That process is called digitization. Digitization. Then this object is represented in terms of 0, 1, 1, 0, etc. like this. And this form is called digital form. And now we store this digital form on our some storage place. After storing, we can process this digital data to get the other information or to enhance the pictures. Suppose we have an image of blurred image, but we want to enhance this blurred image. So to enhance this blurred image, we need the digital value of this image. So this digital image value can be enhanced. And for that, we will use different techniques of enhancement technique, that is known as image enhancement. Image enhancement that has different techniques, and each technique has some advantages and some disadvantages. So after digitization, we process this stored data. We process this stored data, and on this stored data, we apply image enhancement. And after image enhancement, the quality of that object will be improved. And then we will store and transmit that data over the internet to the world. So this is the concept or whole process of our real life image processing. So this is the analog form. This object may be in a solid form or in an analog form. So this analog object is converted into an image by using some projections, and after projections we apply sampling and quantization, then we get digitization, and this digital value is stored and processed. After processing we can transmit this image anywhere. Then output sensors, continuous voltage. This object may be in a continuous voltage if it is in the form of analog. So this voltage is sensed by the sensor. This voltage is sensed by our sensors, and that sensors may be either electrical sensors or magnetic sensors or some physical sensor, etc. That sensors will collect this object, and this sensors, since it it is in the form of analog, so uh, it will produce the continuous image or continuous value. So this analog has continuous voltage, and that voltage is converted into some digital form. So convert continuous sense data into digital form. And image continuous amplitude, x and y has some amplitude, that is also known as intensity, and digital form has sample, that is amplitude samples x and y. So if we convert this image is converted into a pixel. So this pixel has nothing, it has two coordinates. If we place this picture on our coordinate systems, then this pictures has some pixel value. This is our pixel value, and if it is our 0 1 2, this is 3, then 0 1 2 3. So this value or this pixel has some coordinate value. That coordinate values will be obtained by sampling. Sampling will collect the values of our coordinate, and in 2D that coordinate will be x and y. So sampling try to find the values of our coordinate. After quantization we get some pixel value, and that pixel has some coordinate value. So in this picture, this is our 2 and this is 3. So the coordinate of this pixel, if it is denoted by p, this pixel is denoted by p, then the value of x for this will be 2 and 3. So this 2 and 3 is the coordinate value of this point P. And for image, if we convert this point into an image, then it becomes F23, where 23 denotes the 23 denotes the coordinate values at the point P, and F23 indicates the quantized value. This is our quantized value, and this is our sampling value. So the value of coordinate, I mean x and y, the value of xy will be obtained by the sampling. And the intensity, what type of intensity used here, it is dark black or less black, etc. That type of intensity is obtained for this pixel. For this pixel is f2 comma 3. So f2 comma 3 is the function or signal of this point p2 comma 3. Point has only coordinate value, but function has coordinate value, that is 2 comma 3, and its intensity, that is its value of color, is denoted by this function f23, that is known as a signal, and this signal is obtained by the quantization. So this is the some basic concept about the sampling and quantization. After getting this sampling or quantization, we convert this value, or we can process these values according to our requirement. We can increase the intensity, we can decrease the intensity, but the value remains same. We can increase the intensity of this place. Dark image may be less dark, or less dark image may be more darker than this previous color image. So this type of processing will be done on this uh, signal image. How we will take the sample and how we will quantize the value. For that, I have used this figure. This figure may be blurred because I have taken the copy of the PDF, so it is blurred. Sorry. And in this case, this is our real world picture. And if we correlate this picture with our two-dimensional array, if we correlate with this two-dimensional array, then this picture may be divided on different grids, etc. According to the our sensor, according to the our sensors capacity. So this picture is now represented on our graph paper. So how we will sample and quantize these pictures in a digital form? This is the main task. The rule is we follow the each pixel. We will take the value of this pixel plus this pixel plus this pixel plus this pixel. It means we collect the data by some means, or by some device, or by sensors, and store the values. So this is our coordinate 0 0, then 0 1, 0 2, 0 3, and so on. This is our 1 0, 1 1, 1 2, this is 1 3, this is 1 4, this is 1 5, row number 1 and column number 5. So this complete pictures contains a multiple pixels. These are our multiple pixels, and we store the value of each pixels. We store the value of each pixels, and generally there are two different types of values we store. First, we store the coordinate value. That coordinate value is 0 0, and for this pixel it is 1 comma 5, means row number 1 and column number 5. So each pixel has some coordinate value, and that pixel has some intensity. Some intensity means brightness of the color. It may be dark, or it may be less dark, or more dark, etc. That type of intensities at this place. So this pixel, if this pixel is denoted by image element, that is called f, then its coordinate is 0 comma 0. It is the first values. Second, this function has some intensity. Some intensity. That intensity is the brightness of that color. And the color of this may be either a monochrome color, or gray scale color, or color image. So it has some color, and the intensity of this color, the intensity of this color is the brightness, and that brightness is also stored. So we store all these values for this pixel. Similarly, we store all these values for all other pixels. And how we will calculate these pixels? To calculate that values, we use a loop. We use a loop for, suppose this is our y value. So from I equal to 0 and I less than y, we can use a loop for this y value. And this y value we will use a loop, and the maximum value of y depends upon the size of the device. Then we increase the I plus plus. This will give you the column 1, then column 2, then column 3 from left to right. So we will use the left to right concept. Left to right, we increase the pixel one by one from left to right, and then top to bottom, then top to bottom. First we will use the left to right, and this all column will be again in a inner loop of the row. So if we indicate the row by j, then we again use a loop that is j equal to 0 to j less than some value, that is the x value, and we increase the j plus plus. So we will first calculate. If we calculate at this place, then first we will calculate the value of this, then the value of this. Similarly, we calculate each pixel from left to right of the first row. After storing and collecting the all information of these pixels, we increase the value of row. So it will move to the second row, and this second row, all columns or all values of all columns will be stored in our uh, storage place. Then again we increase the j, so we move to the third row, and we use this inner loop, and this inner loop will continue from 0 column to last column. So by using these two loops, we can collect or store the all information of all pixels. So this is the concept how we will find the image of complete object. For uh, for example, I have taken only one row. Suppose this is our one row. So we will move from left to right and top to bottom. In this way, we reach at this place. When we reach on this row, when we reach on this row, we have some different values, and that values is, here it is A, and at this place it is B. At this place the color is, suppose it is a gray color, and this gray color has a color black. So at this place, A, it is white, and it is white till this place, and after that it has some different brightness of this black or some other color. So this has some brightness more than this place. At this place it is less brighter, and from this to this the brightness are changed. The brightness are changed, but from this place to this place again it is white. So it has different gray values, and that gray values is denoted or note we note these values with the help of this graph. At this place it is A, this is B. I am going to take the value of one row, all column of one row. So first we take the all values of first column, then second column, then third column. But for the simplicity, I am taking this example. We come from top row to this row, and at this row we take the values of all column of all these row only. And at this place, from this to this place, it has some other color, that is white. So it is denoted at this place in a white color, since it is in a white color. But as soon as we reach at this place, the color of this pixel becomes more darker than the color at this place. So we come to this place, and this is the darkness place, this is the lighter place, this is the darkness place, and this darkness is gradually increase. So I take the darkest value like this. At this place highlight, and less dark at this place, then less dark at this place, and so on. But at this place it has minimum less than, then it again darkness increases. So this curve bends to the bottom, and after reaching this place the darkness becomes white. So we again jump to this place, and this is the place of B. So this value is represented as at this place, and this value is represented at this place. Since both has the same brightness, so they have same label. But from this point to this point, this row has a different intensity of this black color. So this is shown in this figure. This is called sampling. This concept is called sampling. So I have shown only this line value. I have shown only this line value, and we will collect the all values of all lines that are used to represent this project, this object. So for simplicity, I have taken only one concept. This value is again divided into some slice. This values is divided into some slice. This slice may be uniform or may not be uniform. If it is uniform, then it is called uniform slicing or uniform imaging. And if it is not uniform, it is some higher, some less, then it is called non-uniform sampling. So there are two types of sampling. If this value is broken into a small similar piece or a small equal piece, then it is called uniform sampling. Then it is called uniform sampling. And after getting these sampling values, we have to quantize it. We have to find the intensity. We have to find the intensity of each pixel. What is the intensity at this place, then at this place, then at this place, and so on. So the intensity of each column is represented by the concept of quantization. This is our quantization. This is our quantization. So these values is sampled in a similar stripe, and this value is based on some color model, and we have used gray colored model. So dark color is at this place, then its darkness is reduced from bottom to top. So since at this place black color is less dark, so it is at this place, I mean it is white. And at this place it is more dark, so it has some values. After quantization, why we need the quantization, why we need quantization? If we take the all pixel value at this place, then the number of pixels will be more than this, than the pixel values of at this place. At this place we use only few pixels or few points or few values to represent this object, but at this place if we use, then the number of values will be very very high than this value. So after sampling we quantize it, and this all values has some digital value, that is either 4 or 5 or 6 like this. Then this 4 and 5 is converted into binary number. The binary value of this 4 is 100, and the binary value of 5 is 101, like that. So this has some digital value. So this is the concept of quantization, and I think you will be now able how sampling and quantization is helpful to find to convert the image into a digital form. So this is our real life there this is our real life object, and that object is image on this place. Then we find the value or intensity and coordinate values and intensity of each pixel at this place. Then we sample it. After sampling we quantize it. Then after quantization we convert it into a digital form through digitizer. Digitizer will convert the value of at this place. This has some values. At this place it is 0, then 1, then 2, then 3, then 4, like that. This is our grayscale value, and it will be up to 255. So this 255 values is stored here. If this is our place, then the value of amplitude at this place, the value of amplitude at this place is 4. The value of at this place amplitude is suppose it is 7. So this 4 and 7 will be stored. This 4 and 7 will be stored. Now this 4 digital value can be converted into binary form. 100, I think you know, and this 7, the binary value of this 7 is 111. So this way we can quantize the pictures. After quantization we store this picture in different file format, and that stored value may be enhanced in futures for other processing. So this is the concept. Then after getting the image, we enhance the picture or image, and to enhance the picture we use the concept image enhancement. Image enhancement is used with this transformation, and this transformation technique may be different as per our requirement. This transformation technique is multiplied with the original image. Original image, I mean this sorry, after getting the image from this place. So after getting the image we can apply different transformation on this original image, and that original image is enhanced according to our requirement. So this is the main part for enhancement. Enhancement image is equal to some transformation with original image. Original image is multiplied with the transformation value. So this transformation, and this is our original image. After transforming this original image, we get the enhanced image. Original image is represented by a signal that is called fxy, and this enhanced, after multiplication of transformation, we get the enhanced pictures or enhanced image, and that enhanced image is denoted by g of x y. So this is the original image and this is the enhanced image. There are different types of enhancement technique. We will discuss one by one, and they are asked in our examinations. So first, we want to represent this enhanced pictures, relation between this enhanced image and original image. So if our image is fxy and our transformation method is t, then we multiply these two to get the enhanced image, and that is represented by gx comma y. This original image is r, and this enhanced image is denoted by s. So this r is known as a original gray label, and it is denoted by small r. And this enhanced pictures or image is denoted by capital S, and that is denoted on this vertical axis. And this transformation informations is the diagonal of this value. So this diagonal is denoted by transformation curve, or this is our t. So we can say this r denotes the original value, and this is our enhanced image, and we multiply this original image with this transformation, then we get the enhanced pictures. And if we scale the image intensity on gray scale, if we use gray scale image, then we know that gray scale is of 8 bits. So it has 2 to the power 8, that is L equal to 2 to the power 8, 256. And the range of this 256 is 0 to 255, that I have discussed in the gray label image. Type of image, gray label, we consider in detail about this. So this value is placed on this original x-axis, this original gray label axis, or this x-axis. So the maximum value of this will be 256 minus 256. The L value is 256. So 256 minus 1, that is 255. 255. So our original image value is in gray scale from 0 to 255. This L means 256 because we are using gray scale. So the value of L is 2 to the power 8, 256. 256 minus 1, that is 255. And this value on x-axis is denoted by original gray label. Similarly, we convert this original image in some another gray label, and that gray label is also similar to this gray label. So this is our L minus 1, the maximum value, and it has a value from 0 to 255, because L equal to 256 minus 1, that is 255. So both dimension has same gray label, and it is denoted by 0 to 55, but in notational form, we can write L minus 1. L minus 1, L is 256, and we subtract 1 from 256, so we get 255. So each axis has two different maximum value 255 and minimum value 0. If we draw the horizontal and vertical point on this transformation matrix, we take any transformation matrix point. This is our transformation curve. We take any one point on this curve. If we draw perpendicular from this point to the original gray level and this image gray level, then the scale value at this place will be equal to this at this place. So the gray level of original value image is 50, so the enhanced image will have also same value 50. And this graph denotes the relation between original image and enhanced image. This type of graph is called identical graph, and this identical graph will be used for enhancement technique. In enhancement technique, we will use this identity graph. In identity graph, the value of original image is equal to the value of enhanced image. This graph shows the relation between original image and enhanced image. The value remains same for both. That's why it is called identical graph. Since the value of original image is equal to the enhanced image, so both are identical. That's why this graph is called identical graph, and this identical graph will be used to represent or to use for enhancement, because in enhancement there are a number of technique. In image enhancement, there are a number of technique. That technique uses this identical graph. First image enhancement type is point processing or zero memory operation. If we use or if we want to enhance the quality of image, we will use point processing. Then next is then next is contrast switching, then thresholding, then next is gray level slicing and bit plane slicing. These are different methods: dynamic range compression, power law transformation, and neighborhood processing. So these are power law transformation. All these are part of the point processing. There are two different methods. First is point processing, then there is a method of neighborhood processing. These two processings are used for enhancing the image, and among these, low pass filter and high pass filters are frequently asked in university examination. What is low pass filter and what is high pass filters? Generally, one question is based on either this low pass filter or on this high pass filter. So we will move on this place when we will discuss the neighborhood processing. Before this neighborhood processing, we are discussing about the point processing. And in this point processing, there is no requirement of memory. But in other processing, we need memory location or we need some infrastructure. So point processing has some advantages, and that advantage is if we want to optimize our resource, we want to reduce our resource, then we will use point processing. Otherwise, we will use other techniques. So this is the main part. And now we move to the type of point processing. First is digital negative. The meaning of this digital negative is that if we are if we have a value, suppose if we have a gray value, any point has a gray value, suppose 50, then we will negate it or we invert it. For inverting, we will use the formula S equal to L minus 1 minus R. And L is nothing but the 2 to the power 8, that is 256. So if any cell, if any cell has value P equal to 50, I means gray value 50 at this place, then after digital negative, the value of this will be changed. And to change this value, if it is our R value, then we apply this formula S equal to L minus 1 minus R. And L is nothing but the 256. 256 minus 1 minus R, and 256 minus 1 equal to 255. So minus R at this place is 50. So we get the value 205. So this is the digital negative value of this pixel for value 50. If any pixels has some R value, that R value is subtracted from this L minus 1. And L minus 1, this is always equal to 255. So we can say if the value of any pixel, if the value of any pixel is given, that is the gray value, that value is subtracted from the 255. Suppose a cell has some 100 value at this pixel, then this 100 will be subtracted from the 255. So this will converted into 155. This is the meaning of this digital negative. So we can say original image, if original image is black, then after digital negative, it becomes white. Because if our value is 0, suppose the value of R equal to 0, R equal to 0 means black. And if this value is subtracted from 255, 255 minus 0, then the value of S will be 255. And 255, you know, it is the brightness of color, that is white. It is known as a white. So we can say if R is black, then its digital negative value will be white. And if it is original image is white, then enhanced image will be black. Original image is denoted by R, and this enhanced image is denoted by S. So if R is black, its enhanced value will be white. If original value is white, then its enhanced value will be black. So this is the concept of digital negative enhancement of image. And this has some graph. There is one question on this basis. What are the point processing and what are the different types of point processing? Explain them. So you have to explain all these 7 different types of point processing. And then we will move to the other processing methods. So in this point processing, first is digital negative, and its graph is given here. So this value, if it is our black, and if this value is subtracted from 255, then it will convert like this. And this is our transformation concept that I have discussed in the identity matrix or identity graph. I have already discussed this identity graph. This is our original graph. This is our enhanced graph. And if our curve is from top to bottom, means negative value, then original image is if original image is less white, I means if it is original image is black, then its enhanced image will be white. And if it is uh, original image is white, then its enhanced image will be black. So this is the one two examples. You can take any other values of R and you can find the S value. So this is all about the uh, point processing. Now, second method of point processing is contrast switching. So in this method, bright becomes brighter and dark becomes more darker. It means if our original image is bright, after transformation, this contrast switching transformation, the image will be more brighter. If it is bright, then it becomes more brighter. If it is dark, then it will enhance to more darker. So this is the concept. Suppose uh, how can I use the color value? Suppose it is our color that has gray value 50. Then after this contrast switching, this object has enhanced value, that is 255 more than 50, that is 75 or 75 or 80, like that. So the intensity of this object will be higher due to this contrast switching. So I have written here bright to brighter, dark to darker, and the formula is S equal to L minus R, S equal to M, R minus A plus B, S equal to N, R minus B plus W. Now, what is the value or meaning of this M, L, L, M, R and A, B? If we see this graph, then this is our original image and this is our enhanced image. And this enhanced image has some threshold value. This is our threshold value, V and W. And L, M, N, these are the slope. These are the different slope. This is the value of L, this is the value of M, and this one is the value of N. And this original graph is sliced into two parts, A and B. So it is the A and this is the B area. So this has some region, and that region is between A to B. So after finding or taking these 2 points, this whole system is divided into three regions. It is divided into three regions. First region from 0 to A, second region from A to B, and third region from B to onwards. So these are divided into three regions due to these 2 points. And to find the contrast switching, we use this formula at this place. That is S equal to L minus R. Sorry. We will use this formula at this place. S equal to L minus R. To find the value of enhanced image, we will use this first formula in this first region. And this formula is used in this region. This formula will be used in this region. And the last one for formula, I mean this formula will be used in this region. So all these three values find the contrast switching, but all are based on different region. First region use this formula, second region use this formula, third region use this formula. A and B are the point on the original place, and this V and W are the threshold of the amplitude. This define the sampling is done on this place, sampling is done on this place, and quantization is used at this place. I mean on this dimension. So this is the concept about the contrast switching. Then there is a third type that is called thresholding. Extreme contrast threading. It means if threshold value to find the enhanced picture, we take some threshold value. Suppose our threshold value is 170, like this. If this has 170, so if any pixel has the value p equal to 130, black if threshold is greater than the p value. Since this pixel has value 130, this pixel has 130 and threshold value is 170. Since this value is less than threshold value, this value is less than threshold value, so it the brightness or the color of this pixel will be black. But if this value is 190, suppose it has 190, since this value is greater than this threshold value, in that case this pixel will be converted into white. This is the concept. If the current value is greater than, the threshold value, then that pixel is denoted by white, and if that value is less than threshold value, then it is denoted by black. So I have taken here one example. We take one more example to understand this. Suppose this is our pixel, and this pixel has a value suppose 90, and our threshold value is 180. So what will be the color of this pixel? Since this pixel has less value than this threshold value, so it will be converted into black. But there is one another pixel that has value suppose 200, and this 200 is greater than this threshold value, so this will be converted into white color. This is the concept, where s equal to 0 when original image r is less than equal to a. This is our a threshold value, and if our s equal to l minus 1 when original image is r is greater than 0. If it is this is our threshold value, and if our value is between this range, then it is r is less than equal to a, so the pixel value will be 0 or gray value will be 0. It means the color will be black. And if a point is in this side, then that point will be white. This is the concept. So this is called threshold concept. Then we move to the next type, that is called gray level slicing. This gray level slicing has some advantages. In the previous concept, we are ignoring the background of the picture. Any picture in our real life has some background. So that background may be considered or may not be considered. In the first picture, we are ignoring the background. And in this second figure, we are accepting the background. So by using gray level slicing, we can convert the picture with background or without background. Here, our original image is denoted on x-axis from 0 to L minus 1, gray label, and its value is maximum 255 because L equal to 256. If we divide it into two regions, that is A and B, then this area will be ignore the background. If we want to ignore the background, we will use this area. This is our area of interest where we want to find the background image or not. So to find the background, we will use this concept where S equal to L minus 1 and S equal to 0, no background. And if we want to background, then we will ignore this line. So to ignore this line, the S equal to L minus 1 with background and S equal to R background. If we want to background, then the value of S will be R, and if we want to no background, then the value of S will be 0. So this figure indicates the background image, and this figure indicates the without background image. This is gray label slicing. Then another type is bit plane slicing. Bit plane slicing means if we stored some value in pixel form. This is our pixel form value, and it has maximum value, that is 7. And to denote the 7 in binary, it is in our decimal number, and if we convert it into binary, then it will use 111. This is our binary value, and this binary value has 3 bits. So to represent the value of each pixel, we will use 3-bit concept, 3-bit value. Since in this matrix the maximum value is 7, so if we convert this maximum value in binary, then that binary uses only 3 bits. So we need 3 bits to represent the bit plane slicing. First we find the number of bits. To find the number of bits, we filter, or we search or find the highest value of the matrix. And in this matrix, the highest value is 7, and this 7 has binary value 111. Since it has 3 bits, so all values of this matrix may be represented in 3 bit. Now if we gather this information in matrix form, then we convert this all gray value in 3 bit. So the binary of 1 is 1, but to make it in 3 bit, we will use 001. And the value of 2 is, binary value of 2 is 10, and for 3 bit we put 10 in left hand side. So 010. 3 is 11, but we need in 3 bits, so we put 10. Then 4 is 100. Then 5 is 101. It is already in 3 bits. Then next value is 7, and this 7 is denoted by 111. So if we convert this matrix in binary form, so this 1 equal to 001. So we put here 001, and this 1 is again 001. This 2 has binary value 010, so we place 010. Now I think you understand how we will get this value. And the binary value of this 5 is 101. You can get the value from this place, and the binary value of this 3 is 011, and the binary value of 0 0 indicates 0, but to make it in 3 bits, we use 000. And this 0 is represented here. So we take the binary value of all these. After finding bit value, after finding bit value, we find the bit value from this gray label matrix. From this gray label matrix, we find the bit value or binary value. And this binary value has 3 different columns in each pixel. In each pixel, it has 3 columns. First column, second column, third column. As we know from organization, you know, the left side of the bit, suppose there is a 1 1 1 1, then this is called LSB. The rightmost value is known as a LSB, least significant bit, and the leftmost value is known as a MSB, that is most significant bit, and the other bits are known as middle value. So for each pixel, the leftmost is MSB and the rightmost is LSB, and remaining, I mean this, is the mid. So first we find the gray value of any pictures. Then after getting this gray value, we find the highest value of that gray code, and we convert this gray code into binary number. We find the number of bit. If it uses 5 bits, we use 5 bits for all other gray value, and if it is 3 bits, uh, then we will convert the all pixel or gray value in 3 bits. So first we find the gray value, then we convert this gray value in 3 bits, and after getting 3 bits, we slice it in different form like MSB, LSB, and middle. In this case, there are only 3 situations: most significant, least significant, and middle. But if it is in 5 bits, in that case, suppose it has 5 different values, then we will we will make 1 2 3 4 5 different slice. First for this, second for this, then third for this, fourth for this, and for this. So we will 5 values, but since it has 3 bits, so there are 3 slices, and this slice is nothing. This slice is nothing. We put all these values of first column at this place. We take the MSB of all column 0 1 1, then 0 0 1, then 0 0 1 in LSB slicing. So this 0 0 1 is placed here, this 0 0 1 is placed here. Then we take the middle value. We take the all middle value, all these middle value, all these middle value at one place. Then it is called the mid slice. That is 0 0 1 0 0 1 1 0 0 1 0 0 0 1 1 0 1. Then we take the LSB value, and this LSB value is this one, 1 1 0 0 1 1 0. So 1 1 0 0 1 1 1 1 0. So we get these 3. Now what is the use of this plain bit slicing? If we send this information in gray value, anyone can understand the meaning. But if we convert it into bit plain slicing, if we convert it into bit plain slicing, then this LSB value has the all this MSB value. Sorry guys, this is our MSB misrepresentation, and this is our LSB. Sorry, this is our MSB. if we send this MSB value only of all column, then no one understand what is the meaning of this, because it is the part of each column. And after getting this LSB, someone can guess what is the meaning of this complete transformation. So this this bit plane slicing may be used for security purpose. This bit plane slicing may be used for security purpose. Then next is dynamic range compression. Time is over. Are you interested, or we will continue tomorrow? Hello. Okay. Okay, guys. Please switch on your camera so that I can take image. Please switch on your camera. Yes, please switch on your camera to take the image. Okay, guys, thank you. We will meet